Already. Good morning, everybody. Welcome to another sunny, warm morning, Chem 1211, with your host, me, Dr. White. And we got a lot to do, so I better start doing it. All right, let me remind everybody that this Wednesday after class, I will send out the password for test number two. Test number two covers everything dealing with chemical bonds and mole type relationships, and also balanced chemical equations. I've already talked about what's covered in the points. You've been sent an email, and it's also in the announcement in Blackboard. On sometime Tuesday afternoon, I will post test number two PDF file. Actually, I'll do two of them, and half the class will do one, the other half will do the other. And I'll be, like I said, Wednesday afternoon, right after class, or not afternoon, Wednesday morning, I'll send out the password for each version to whoever gets what. And you'll have until Thursday morning to take the test, do your answers, and upload your answers to Blackboard. All right, another thing I'd like to talk about, and that's the labs. I said Sunday was the cutoff. I'm going to give everybody until tomorrow, 1 p.m. to hand in your labs. If you can't find a link, email me the labs. Starting this Thursday and Friday labs. If you're late, you got until Sunday, 1 p.m. to hand in your labs. If it's after that, you get 0 points, which is not a good thing. So please hand in your labs when they're due. All right, what are we going to do today? Well, first of all, I'm going to do my world famous review for the next test, test number two. And after that, we'll go back to working on gases. Oh, by the way, I finished yesterday. How should I say? I improved it. The lab this Thursday and Friday, you'll get a bang out of it. Literally, you'll love it. Modest, aren't I? All right, let's get to work. Everybody see test two review on your screen? Thank you. All right, we talked about atoms. In the nucleus are the neutrons and protons. Where are the electrons? They're all around the nucleus, and they're in the electron shell. And each shell, the electrons in the shell have approximately the same amount of energy and approximately the same amount of distance from the nucleus. Now, shells have names, and they're very fancy: 1, 2, 3, and 4. And each shell has subshells. A subshell, which I'll never ask you what's a shell or subshell on a test, but a subshell is an area in a shell where all electrons have the same amount of energy and are the same distance from the nucleus. And shell 1 has 1 subshell. Shell 2 has 2 subshells, and shell 3, 3, and 4, 4. And when we talk about shells, shell 1 has the lowest energy. And it increases where shell 4 on this table has the highest energy. One thing I talked about, this table, but not this part here about the energy, will be given to you in important information test number 2. In the past, students have to memorize it. I'm no longer doing that. I'm just testing your skills in chemistry, not your memory. Now, the subshells have names S, P, D, and F. They actually use letters. Nobody uses the actual name for them anymore. And S is the lowest, F is the highest. Goes from S, then P, then D is higher, then F is the highest, as I showed here. Now, subshells, excuse me, have only a certain amount of electrons you can put in there. I don't know why, even though you write them all, let me do it cap. Well, actually, I do have them lowercase. They're actually written lowercase. If you do upper lowercase, I don't care. Now, a subshell, there's only a certain amount. Subshell S, you can only put 2 electrons, P 6, D 10, F 14. Now, once again, as I have up here, S is the lowest energy. And F is the highest energy. Now, one of the things we talked about, and I showed you how to do, that's called the electron configuration. That's a statement of how many electrons an atom has in each of its subshells and shells. Remember, a subshell is named by a number and a letter. Again, a subshell is named by a number and a letter. And for electron configuration, in number, letters, and superscript numbers. So let's do an example. Everybody see my whiteboard? Yep. All right. So the question is, write the electron configuration for carbon. And how do you do carbon? Well, first of all, remember, electron configuration is for all the electrons. I'll say it again. Electron configuration is for all the atoms, electrons in an atom. And how do you find that out? You go to your neighborhood, friendly neighborhood periodic table. Everybody see the periodic table? Thank you. And you look for the atomic number. And that's the number on this one, which you'll be given for test number 2, just like I gave you this for test number 1 to download, is 6. That means carbon has 6 electrons. So we now know we have 6 electrons. And let me put over here shell number of subshells. And I'll put this other table, only do the first 2 entries. Psst, don't forget my gift to you. Remember, you're only going to have to know how to go up to magnesium for electron configuration. Shh, don't tell anybody my gift, but you only have to go up to magnesium, which means you only have to know how to do the S and P orbitals. Shh, don't tell anybody I said that. All right, let's do the electron configuration for carbon. And we start with the lowest energy shell, which is 1, and its lowest energy subshell, letter number 1s. How many electrons can I put in any s subshell? 2. Well, you show it that way. Well, I've got 2, but I got 4 more to go. And at 1 has only 1 subshell. I filled it. So now I have to go to the next subshell, which is 2. I just thought about something. You will need to know 3, not for this problem. And the first subshell in 2 is, remember, number letter 2s. How many electrons can I put in 2s? 2. Well, I just did that. And then we filled it up, 2s. But we have 4 electrons, 2 plus 2, and 6 minus 4 means we have 2 more to go. And I filled up 2s. How many subshells does 2 have? 2. The first one is s, the second one is p. Since it's 2, it's actually 2p. And how many could I put in there? 6, but I only have 2, so I can do that. And this is your answer. And that's how you do electron configuration. Now, when it comes to electrons, the most important, in my opinion, is the valence electrons. And you should know that the valence electrons are the outermost electrons of an element. And the other thing you should also know is the number of valence electrons for an element is found on the top of the column of the periodic table. And therefore, let's look at a periodic table. If we look at the periodic table, you'll see, and this is the one you'll be able to download. It has both Roman and numeric numbers. And notice for carbon, IV, which is the Roman numeral for 4, tells me I have 4 valence electrons. The maximum you can have is 8. Argon, look up here, VII, 8, or the number 8. So that has 8 valence electrons. Now, when we talk about valence electrons, we show that by doing Lewis structures. And you should know how to do a Lewis structure. We did this. How do you do a Lewis structure? For elements, this is important. For elements, use the element's chemical symbol. Use only valence electrons, common mistake. Students use all electrons. Nope, you're using only valence electrons. And you put 1 dot, 1 valence electron on each side of the chemical symbol as a dot before doubling up. So and so if I were to ask you on a test, say 3 points or 2, whatever, draw the Lewis structure for oxygen, the first thing you have to know is how many valence electrons does oxygen have? And if we go to our favorite periodic table, here's oxygen, symbol is O. Look up on top, it has 6 valence electrons. And therefore, I know I have 6 valence electrons. Put the oxygen one dot on each side for each of the four, and then you double up. And two sides will have two, and two sides will have one. Organic chemists like to double it up this way. I'm an organic chemist, so that's one of four possible answers. And that's how you do Lewis structures. Next thing I talked about was the chemical bond. And chemical bond are the forces that hold atoms together in molecules. Oops. There. And there's two types of chemical bonds, and those are ionic and covalent bonds. And you should know that an ionic bond results from the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. And a covalent bond results from the sharing of one or more pairs of electrons between atoms. And I won't ask ever on a test, but you should understand the octet rule. In compound formation, in other words, making chemical bonds, atoms of elements lose, gain, or share electrons in such a way that their electron configuration is identical to that of the nearest noble gas in the periodic table, which is 8 valence electrons. Now, when you gain or lose an electron, you form an ion. And how do you do that? Determine what ion an element will form. Elements lose or gain, so they have the same number of electrons as the nearest noble gas. Therefore, calcium, what ion does calcium form? If you look at the electrons and protons, remember atomic number gives you number of electrons, number of protons. In an atom of an element, and the atomic number for calcium is 20. So it has 20 electrons and protons. The nearest noble gas, let's take a look at the periodic table. Here's calcium. The nearest one is argon with 18 electrons. And therefore, it wants to have the same number of electrons as the nearest noble gas, argon at 18, but it doesn't change the number of protons. And remember, each electron is a -1 charge. Each proton is a +1. Looks like an H, but that's really a +1. See, it's a +1. But anyways, 18 times -1 is -18. 20 times +1 is 20, plus 20, add them together, +2. And if I ask draw the ion, what ion does calcium form? You show the chemical symbol, then to the right superscript, you put the charge. And I like doing the old fashioned, putting plus first, then the number, and newer way, the last 10, 15 years, yes, I like the real old way, is 2, then the charge plus. Now, when it's a +1, you just, or -1, you show the sign, no number. Now, when we talk about charges, ionic compounds form when you have transfer electrons, like in sodium chloride. And when we ask for draw the formula or the empirical formula of an ionic compound, this indicates the number and kind of ions. And the most important thing, the ionic charges always add up to 0. In any molecule, every molecule in nature has a net 0 charge. Therefore, This is a plus 1. This is a minus 1. And it adds up to 0. So the formula for sodium chloride is NaCl. It should be an and, not a plus. So what would be the empirical formula for a compound with calcium plus 2 and chlorine minus 1? I'm going to let you try this one. I don't want to share the fun. All right. I'll bet everybody's done. And how do you do that? Let's take a look. Calcium has a plus 2 charge. Chlorine has a minus 1 charge and has to add up to 0. You can't change the charge, but you can change how many of that element is in the molecule. To add to 0, we need 2 chloride anions. So what does this tell me? I have 1 calcium and I have 2 chlorine. And that's the stuff in the little white pellets hopefully we won't need until next December, or better yet, next January. Now, when we talk about Lewis structures for molecular compounds, we talk about bonded electrons. Those are pairs of valence electrons that are shared between in a covalent bond. Now we're talking about a covalent bond, which is sharing pairs of electrons. And you have non-bonding electrons pair, and I'll never ask you what's a bonded or non-bonding, but I might ask you to circle them in a structure. And those are pairs of electrons not involved in electron sharing. Now, when it comes to covalent bonds, know this. There are 3 types of covalent bond. The first one is a single bond. And a single bond shares 1 pair of electrons. The second type you should know is a double bond, and it shares 2 pairs of electrons. And the third is a triple bond, and it shares 3 pairs of electrons. Single bond, 1 pair, double bond, 2 pair, triple bond, 3 pair. And when you're drawing a Lewis structure of molecules, remember, if a molecule has an alkali metal or alkaline earth metal, these will never, ever be in a covalent bond. They give up their electrons and form ions, like sodium forms a plus 1, same thing with potassium or lithium. I see a question. The answer is yes, I can repeat it. When you're doing the Lewis structure of a molecule, if you have an alkali metal or an alkaline earth metal, which you learned in test number 1, this column or this column, then these always give up electrons, like lithium forms a plus 1, sodium forms a plus 1, potassium forms a plus 1, magnesium and calcium plus 2. And they always give up electrons. So what does this mean? Let me do 2 quick examples. Ah, come on. I was going to write nitrogen gas. Now, nitrogen, when we're talking Lewis structure for a molecule, you need also to go valence electrons. Nitrogen has 5 valence electrons. There's 1 nitrogen. There's the other. And this nitrogen says, I've got 3 unpaired electrons. You've got 3 unpaired. Let's share. And they do. Now, unlike the Lewis structure for an element, for a molecule, you can have more than 2 electrons on a side. And if we look at this nitrogen, shared and unshared electrons, it has 8. And if we look at this nitrogen, it also has 8. And what kind of bond is that? 3 pairs of electrons? It's a triple bond. All right, now let's do another one. Sodium hydroxide. Immediately when I see an alkali metal, I know that forms this. Now, remember, sodium, 1 valence electron, oxygen, 6 valence is on the periodic table, hydrogen, 1 valence electron. Now, oxygen has 6, and hydrogen has 1 unpaired valence electron, and it says to oxygen, let's share. And they do, and they form a single bond, 1 pair of electrons. Now, hydrogen's octet is 2, so it's got it. But if you look over here, oxygen only has 7, but where did this electron go to form this charge? It goes to the oxygen, and now oxygen has an extra electron and forms the hydroxide anion. And that's how you do Lewis structures of molecules that have alkali metals or cations and anions. All right. Now, next, I started talking about the mole and mole calculations. And you should know what is a mole. Huh. I tried something new and it's not working. There. And a mole is a chemist counting unit. And there are other definitions I can also use for a mole because I taught you these important relationships. Now, this stuff will be in the important information test number 2. I used to make students memorize this. I don't anymore. And here we have 1 mole of an element equals Avogadro's number, and that should be 6.02 times 10 to the 23rd. Let's see if I can do something here real quick. And same thing here. All right. Now, you should know 1 mole of an element equals 6.02 times 10 to the 23rd atoms of an element. And you should know 1 mole of a compound equals 6.02 times 10 to the 23rd molecules of that compound. And I showed you how to convert from moles to molecules, or moles of an element to atoms, or moles of a compound to molecules, and back and forth again. And how do we do that? We used your good buddy, your good friend, unit analysis, which we went through the practice problems here. You should know 1 mole of an element equals the atomic weight of that element in grams, and 1 mole of a compound equals the molecular weight of that compound in grams. And remember, the sum of all the molecular weight of a compound is the sum of all atomic weights in a compound. And as I have right here, remember to use your good buddy, your good friend, unit analysis. On test number 2, underneath where you put your name, it will say, please use proper significant figures for all calculated answers. And it will also say now, please use 3 significant figures for all atomic masses. If you don't, I'll take off a point. So please follow instructions. Oh, I'll mention it on Wednesday, but it pays to show your work. As the Friday lab pointed out, and so I didn't, but anyways, there are a couple of mistakes, problems 7 and 10 on the chapter 8 problem set. Dr. White messed up, sort of. I've written the test and did all the answers already, and there's no gray areas. It's pretty straightforward, your calculations. But if you transpose the number, write the wrong number down, or round off wrong, instead of getting 0 points for not showing your work, which I will do, if you show your work and I can say, oh, you made this little math error or rounding error, if it's a 10-point problem, I'll only take off 1 point. So be sure to show your work. Now, in this chapter 7, we talked about, notice I say we, I did and you listen, but I like to say we anyways. We talked about the chemical equation. And here's a chemical equation. We have an arrow. At the base of the arrow are the reactants, which I also will call starting materials. At the head of the arrow is the product or products. Now, because of conservation of matter, you have to have, in a chemical reaction, you never create or destroy atoms. You just swap things. And doesn't sound scientific. Things are interposed. Ooh, that sounds better. And what that really means is you have the same number of atoms and the same type of atoms on both sides of the arrow when you have a balanced chemical equation. And I taught you, when you're balancing a chemical equation, you have to have the same number and same type of element on each side. I don't know why I have that extra 1 on each side of the chemical equation. And you can only change the coefficients. You can't change the chemical structure. Now, my advice to you is leave hydrogen, oxygen last. And I also taught you in lab and in classroom the even odd trick. If you have one side as a molecule of even number of an atom, the other odd, how to deal with that. Now, there's something very important I need to show you. I taught you before, but I should do it again. Now, this is a balanced chemical equation, and the coefficients, the numbers in front, are always whole numbers, which hopefully you realize by now, exact numbers. But if you can divide all the coefficients by one number and get whole numbers, you should. So if I were to have something like this, even though it looks balanced, is wrong. And I'd give you 0 points. Why? Because you can divide each of the coefficients by the number 3, and that will take you back to this balanced chemical equation. So make sure you can't divide all your coefficients by the same number and get a whole number. And you keep on doing that until you can't. And that's the difference between this, and that's why this is wrong, this is correct. Again, you can't change the formula, but you can change the number in front. And the answer everybody want me to repeat it again is, of course, I can repeat it. Oops, see someone else asking a question. All right. Convention chemists use is when you're balancing a chemical equation, if you can divide all the coefficients by the same number and get a whole number, then you should. And you keep on doing that until you get an equation where you can't divide all the coefficients by the same number and get a whole number. You can't divide 1 by 2, where you can do it here and get 1, here and get 1, but 1 divided by 2 is 1/2, which is not a whole number. But the wrong one, I could divide each of these by 3. And when I do that, I come up here. Another example would be, let me think about it. This would also be wrong, because if I can divide all the coefficients by a number and get a whole number and can't divide those anymore, then I'm at my balanced chemical equation. And notice if you divide each one of these by 4, that will bring you up to here. And that's the convention chemists use. And that's why I would mark the bottom 2 wrong and the top 1 correct, even though each of those has the same number and same type of atoms on each side of the arrow. You're welcome, Kelly. And anybody else who asks questions. Remember, I think you know by now, there's no such thing as a don't question in my course or in my life. Now, using a balanced chemical equation, first of all, you should know that the coefficients of a balanced chemical equation give you molar ratios. Let me write this one again here. Oh, by the way, for test number 2, there'll be 4 problems on balancing chemical equations. Ooh, I better tell you this. If I asked you to balance a chemical equation on a test or a final, you're going to have to balance it. The answer, it's already balanced on my test or final, will never, ever, ever, ever be correct. You really will have to balance it. So just wanted to make sure you know that. Oh, by the way, notice I'm in a short sleeve shirt. 1, it's warm outside. And 2, good news. Today, this afternoon, I'll be getting my first vaccination. I've been trying for like 3 weeks to get an appointment. All of a sudden, it was a Thursday or Friday, through the medical group I belong to, Northwest Community Hospital. Yes, thank you, Gabriella. And all of a sudden it opened up and the first available was Monday afternoon, and I just jumped and took it. And luckily it's only about 10, 12 minutes from my house, which is also good. So Dr. White will be protected in a couple of weeks. Next couple of weeks, I'm gonna be real careful until I get my second shot, and then 2 weeks after that. And still, I'm going to wear a mask and be careful. All right, back to this. What does this mean? The coefficients of a balanced chemical equation give you molar ratios. What this really means is 2 moles of hydrogen, and when there's no number, the coefficient is 1, react with 1 mole of oxygen to make 2 moles of water. Remember, the balanced chemical equation, gives you molar relationships. And then I taught you, and we went through that last Thursday and Friday. If you weren't there, look at the videos on Blackboard on YouTube. Interesting. They used to post Blackboard videos, some teachers, and about a month ago, the college decided, this is taking up too much space. We're going to have faculty stop that. Luckily, I stayed away from that and went to YouTube, so I don't have to worry. Anyways, I taught you, if I were to ask you, if you're at 5.00 grams of hydrogen with an excess of oxygen, how many grams of water you use, there's no way you can go from gram to gram. And therefore, what you use here is mass calculations. Remember, mass is grams. And how do you do that? There's a 3-step, and this I will give to you. This is on important information, test number 2, which will be at the back of your test, last 2 pages, and the mass calculations. Step 1, whatever you're given in grams, you convert to moles, which you've learned how to do, I hope. Once you get that to moles, you convert from moles of A to moles of B using the balanced chemical equation to give you molar ratios. We did that Thursday and Friday. Hopefully you've practiced that. And then finally, once you get the moles of B, you take the moles of B and convert it to grams of B. And as I state here, remember that the coefficients of balanced chemical equations are molar ratios. And once again, use your good buddy, your good friend, unit analysis to do that. Now, the final thing that I talked about for this test number 2 is limiting reactants. And limiting reactants determine the number. You have 2 reactants, and you're trying to find out which one runs out first, and that determines how much of the product you could make. And how do you do that? For each reactant, determine the number of moles of a product using the moles of each reactant and the balanced chemical equation and the relationship that coefficients of a balanced chemical relationship are molar ratios. And you'll get 2 numbers. Always in my problems, let's do 2 reactants. I could do more, but that's enough. And the lower number of the product formed from each calculation is the answer. And that's my review for test number 2. Any questions? Know something? Instead of rushing through a problem when we get back to gases, let's take a 5-minute break now. Oh, Gabriella asked an excellent question. The review sheets that I just went through have been available all semester in the lecture folder of Blackboard. Biljana, at least one. I don't know exactly how many, but I would bet at least one. Oh, by the way, did I tell you? Shh, if I say I bet, I know I won. Any other questions? All right. Let's take a 5-minute break. Now it's 10:46. Come back at 10:51, and we'll continue with, yes, electron config. If I go over it in a review session, hint, hint, wink, wink, say no more. You guys should look that up on Monty Python. That means yes. With that, I'll see you at 10:51, and we'll continue. Oh no, I'm running late. Better use the get back to class whistle. I think I have to replace the batteries. There. All right, let's get going. All right, any last minute questions on test number 2? If you do have any questions, remember tonight I'll be having my office hours, and if you need any help with anything, please stop by. That's from 6 to 7:15 on Zoom. So with that, let's get back to gases. Remember, the gases that I went through like last week will be on test 3, not on test number 2. Oh, that reminds me. Did anybody happen to feel the wind on their face? If you were out yesterday enjoying the weather, think about that's gases hitting you, molecules of oxygen, nitrogen. It's chemistry. All right, we already did Boyle's law, P1 equal V1 times P2 equal V2. And remember, the gas laws are dealing with important parameters that you can measure for gases. And where is this important? Well, it was in the steam engine. It's now in the gasoline engine, combustion engine. Now, let's go on. We did Boyle's practice time last time. So let's move on. All right. Click Charles' law. I'm turning a switch. Will this be on a test or final? Click to the off position. But I still want to mention it. And Charles' law is the volume of a sample of gas is directly proportional. This is important for gases. It's Kelvin temperature if the pressure is kept constant. Remember, a balloon left outside in the winter. Okay, I will. Now, what Charles' law really is V1 over T1 equal V2 over T2. This will not be on test, but I just want to mention it. V1 initial volume, T1 initial temperature in Kelvin. So if you have Celsius, you have to convert to Kelvin, which you know how to do. And this is equal to V2 over T2, where V2 is the final volume and T2 is the final temperature. Now, if I were to give you 3 of these, like V1, T1, and then give you V2 and ask you to solve for T2, over the years, just about every student of mine got it wrong. So I decided I'm not going to put it on a test or a final because everybody gets it wrong. And there are more important things I like to talk about. If you were chem majors, I expect you to learn how to do the math, but you're not. Now, the interesting thing, this is why I say, remember the balloon. How many of you have ever gotten those party balloons? They're all nice and full, and it's winter time, and you decide, oh, I'll put it outside on my balcony if you live in an apartment or a condo, or on my railing outside my front or back door, because I don't have really room in my house. And it's cold out, and next morning you say, oh no, it shrunk. It must have a leak. No, that's because of Charles' law. It got colder, so the volume decreased. And that's why that happens. And again, Charles' law and any gas law, we're using temperature. It's always going to be in Kelvin. Remember, Kelvin equals degrees C plus 273. Oh, it even says it on the slide. It must be true that it won't be on test number 2 or the final. All right, click, switch is still off. they have what's called the combined gas law, dealing altogether with volume, temperature, and pressure. And that's this, where it mathematically combines both Boyle's and Charles' law. And this is P1 V1 over T1 equal P1 V1 over T, that should be a 2 right there. Just got it. P2 times V2 divided by T2. Yeah, all right, let's do it again. P1 times V1, pressure volume, divided initial temperature equals the final pressure times the final volume divided by the temperature, final temperature. Now, this I've never used, but this can be derived by the ideal gas law. See next slides. Again, this will not be ever on a test or final line. Same thing for this slide. This is Avogadro's law. And what Avogadro made famous was, and why he's 6.02 times 10 to the 23rd is named in his honor, because he found the relationship between the volume of a gas and the moles of a gas. How many you have? And that's the equation V1 over N1, N being initial moles, V is initial volume equals final volume and final moles. And this is can be derived by the ideal gas law also. And I think I mentioned it later, but in case I don't, Avogadro found that STP, standard temperature and pressure, 0 degrees C, 1 atmosphere, 1 mole of a gas equals 22.4 liters. That won't be on a, and that's where he found the relationship between moles of a compound and a measurement of a gas, and he was the first one to do that, which is why they named 6.02 times 10 to the 23rd Avogadro's number. If I had a dial that only went up to 10, I've just turned it to 1,000. Click, switches on, and it's all the way, all the way. Let's talk about Dr. White's favorite, favorite mathematical expression in all of chemistry. Mathematical, not chemical reaction, but mathematical expression, and that's the ideal gas law. And the ideal gas law is PV equal nRT. And P is pressure, but it's always in atmospheres. V is volume, and it's always in liters for the way I teach it. N is the number of moles. T is the temperature, and for this, it has to be in Kelvin. And R, right here, R is called the universal gas law constant. And for this class, I use these units. R is 0.0821 atmospheres liters per mole Kelvin. And this is a calculated number, so this is 3 significant figures for R. If you notice, I didn't even have it on the slide. Learn this. Running out of room there, so I'll put it on this side. Remember, 3 stars and the word abbreviation important with an arrow tells you better know how to use this, because Dr. White loves the ideal gas law. And the ideal gas law gives you a relationship between pressure and volume of a gas and the number of moles and its temperature. And this turns out to be very important. Now, in my own life, PV equal nRT in yours too plays an important role that you should be aware of. And I'll write this on the whiteboard, but let me do it first. And that is your car tires. Your car tires are full of gas, unless you have something brand new that I don't know about. And that gas usually is air, or could be nitrogen or oxygen. And that keeps it inflated. Now, many years ago, I lived in another part of Schaumburg, and I had an apartment I was renting. I hadn't bought my house yet, and therefore I parked outside in the parking lot. And that winter, I think it was somewhere around 84, 85, 1984, I had an Explorer. I've had an Explorer since 1990. So it was about then, somewhere around then, 85, 90. I've had a couple Oldsmobiles, and then the rest were Explorers. I like four-wheel drive in the winter around Chicago. It's nice. But anyways, I had my Explorer out in the parking lot, and that's Friday night. The outside temperature got down to like 20 below Fahrenheit. That wasn't the wind chill, that was the actual temperature. I figured the next day I'll get up early in the morning, Saturday, about 7:30, and go out and drive my car for about 15 minutes because the temperature affects your battery. And I'll teach you that later in the semester, how it affects it. But anyways, I go out to my car and it's in a parking lot, and I look at the tires and say, oh no, I have four, not one, not two, not three, four flat tires. What happened? Because the air was really low. And it took me about 2 seconds. All of a sudden said, ideal gas law, PV equal nRT. And immediately I went over to the local gas station. Luckily, I was up earlier than most people, and started filling all my tires so they'd be inflated properly. By the time when I pulled up, I was the only one in the gas station for air. And by the time I finished my tires, and I'm pretty quick at filling air in my tires, I have a good gauge and I can do it pretty quick. After a couple of minutes, I look up, there are at least 10, 12 cars in line waiting for the compressed air pump. That's back when it was free too. And how did PV equal nRT teach me that? How did I know? Well, let me show you. Today's Subtle Monday. PV equal nRT. Remember, P is pressure, V is volume, N is the number of moles, R is the universal gas constant, and T is the temperature. Well, in winter, if I could spell it right, what happens? The temperature gets cold, it goes way down. Well, if you have PV equal nRT, and this really should be a lowercase n, in your tires, unless you get a flat and then all bets are off, and hopefully you don't, because I've done that, they're not fun. V is constant, the moles is constant, and R is the universal gas law that's constant. So in the winter, if the temperature goes way down, the only thing on this side that can change is the pressure. So in the winter, when the temperature gets real cold, your pressure in your tires gets lower because PV equal nRT. This side has to equal this side, and the only thing that can change in your tire when it's not got a flat is pressure and temperature. Now, back in this, I remember, because where I was working, in the summer of 95, in the Chicagoland area, we had a brutal heat wave. That's when the daytime temperature for almost 2 weeks stayed above 100 degrees Fahrenheit. Uh, Sadly, I think about 500 or 600 people died from the heat problem. And that's when now governments have cooling places if it gets real hot for a long time, where our citizens can go if they don't have air conditioning. And back then, I lived in Schaumburg, but I worked in a company that was near Great America and Gurnee. So I'd take the expressways there. It was an hour trip each way in good weather. Winter, that's another story I'm not going to tell. But anyways, that summer, when it got hot like that, me driving either there or back, you'd see all along the road, trucks and cars with blowouts. Why did their tires blow out? The heat and PV equal nRT. How did that happen? Well, in the summer, what happens? The temperature goes way up. And that summer, unfortunately, it really did. And PV equal nRT. In your tires, V stays the same, the volume, the number of moles doesn't change, and this is the universal gas law constant. So the only thing that can change is the temperature. And if the temperature goes way up, to keep this equal and V can't change, the pressure goes way up. So in the summer, when the temperature goes up, you better check your car tire pressure, because if it goes too high, just like if you fill a balloon too much, it explodes, goes pop, more than pop. And that's not a fun thing. Therefore, you should know in the winter, when it gets super cold, you should check your car tires pressure, because PV equal nRT tells you temperature goes down, pressure goes down. In the summer, you should know when it gets super hot, check your car tire pressure. Why? Because the temperature goes up. I like my great hand demonstration, and the pressure goes up. So PV equal nRT tells you the winter and the summer, you should check your tires. And you should know that, because you don't want to get a flat, or you don't want to look, oh no, it looks like I have a flat tires. That really, it took me about, I'd say almost a minute before all of a sudden this part of the brain said, come on, you're a chemist, PV equal nRT. And I said, oh, I better go fill them up. I beat everybody to the gas station. Now, the important thing to remember about PV equal nRT is each of the variables, when you're doing a calculation, has to be in the right units. Again, when we're doing a PV equal nRT problem, each of the variables has to be in the right units. Pressure has to be in atmospheres, volume has to be in liters, moles, N is in moles, and T is in Kelvin. Now, generally, most gauges I've ever seen, like all of them, measure either torr or millimeters of mercury. So you'll have to convert that to atmospheres. Now, my problems always give you liters, but I've never seen a balance that does moles. It's grams. And you know how, hopefully for test 2, you better know how. I shouldn't say you better, it'll be quite beneficial. You won't lose a lot of points, how to go from grams to moles and moles to grams. And finally, temperature, you learn in test number 1 that I've never seen a thermometer or gauge in Kelvin. It's always in degrees C, centigrade, and therefore, or Celsius, I keep on using the old name. Therefore, you need to know how to convert from centigrade to Kelvin. That will be given to you. Also, the universal gas law constant is 0.0821. That will be given to you. This whole thing right here in test number 3, useful information. I used to make students memorize it, but not anymore. You just have to learn how to use this. Let's have some Dr. White fun with PV equal nRT. When you burp, you get what comes out of you mainly? Carbon dioxide. So let's have fun with burps. Bet you never thought you'd get into burps in my class. You do. Wait, I even get into other things too. All right, pay attention. Yep, that's right, 15 points. Hold on, give me a second. I want to rewrite this. As one of you asked, can you translate what you just wrote? And the answer is yes. Let's look at this. 15 points. Yes, 15 big ones. If you burp 0.521 grams of CO2 at 751 torr and 24 degrees C, then what is the volume of your burp? Let's do that again. If you burp 0.521 grams of CO2 at 751 torr and 21 degrees C, then what is the volume of your burp? Everybody got that written down? Rest of you people, you got that written down? And those of you turning on your camera, thank you. Liliana asked, will you get it ever in degrees F? In my class, no, because that's just an extra busy step. All the years I've doing chemistry, when you're in a chemistry lab or a chemical plant, well, chemistry lab, measuring any kind of gases, you're always in degrees C, centigrade, Celsius. I keep on using the old name. So that answers your question. All right, how do you do this? First of all, what are you being asked to find? Volume. What are you given? Ooh, a weight, 0.521 grams of CO2 gas. And what are you given? Ooh, torr is a pressure. And you're given degrees C of temperature. And where do you find a relationship between all these? PV equal nRT. And what are we solving for? V. Remember, P is pressure and atmospheres. V is volume in liters, and I'll always give you liters. N equals moles. R is the universal gas law constant. Atmosphere liter per mole K, Kelvin. And then T is temperature. In Kelvin. Now, the first thing I want to do is, how do you solve for V? How do we get it alone? When you have a multiplication, I want to get rid of P so I can divide both sides. If I divide this side by P, anything divided by itself becomes the number 1. So that cancels out. But whatever I do to one side, I have to do to the other. So now we have volume equals nRT divided by P. Well, I can't use these numbers. Why? Because they have to be in the right units. So let's start with pressure. Pressure needs to be, let me move myself out of the picture here, in atmospheres. So let's give us some room. You'll be given one atmosphere equals 760 torr equals 760 millimeters of mercury. So how do I go from this, which I have 751 torr, I want to go to atmospheres? Well, here's what I'm starting with. Here's what I'm ending up with. It's time for Dr. White to say, it's time to use your good buddy, your good friend, unit analysis. And whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. In this case, where do we get these numbers? We come over here. Well, first of all, we write them in, the units. And we have one atmosphere is 760 torr. And now torr cancel out and I'm left. Remember, 1 and 760 are exact numbers. Therefore, this is 3 significant figures. My answer should be 3 significant figures. Now, this is one of those cases where we'll be doing multiple calculations. Hold on, didn't open up the right thing. And when we do multiple calculations, you can round off at each step or round off at the end. Ah, come on. I'm getting there. Mean right here or right here? Right or left? Right here, 1 subscript atmosphere. That means P has to be in atmospheres. Over here on right, 1 atmosphere equals 760 torr equals 760 millimeters of mercury. And therefore, if we come over here, we know this has to be an atmosphere, P subscript atmosphere. This is my way of telling me that's the units I have to have the pressure in. And all questions are good questions. You're welcome, Kelly. So I'm going to come and say I need to divide 751 by 760. So I'm going to go to my calculator. I just wanted to close the window because it's, all right, go to my calculator and come up here and I do plus 751 divided by 760. Now, there's 2 ways, and I'll calculate both ways on my tests and finals to round, either round off at each step or round off at the end. And by now, you should know I'm a round off at each step person. So I'm going to round that off to 3 significant figures, and that's 0.988. So I can write here my pressure in the atmosphere is 0.988. Well, I've got that done. And PV equal nRT, R, which is going to be given to you, that's done. I'm going to do temperature next. I need temperature in Kelvin, which is equal to degrees C plus 273 equals, what's my temperature in Celsius? 24. Remember, when you're adding, you have the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right. But in this equation, 273 is an exact number. It's part of a definition. This has 0. Therefore, my answer will be 297K. So I've got my pressure, I've got my temperature, I've got R. Now I've got to do N. Now what is N? N is moles. Oh no, I don't have moles. I have grams. So what do I have to do? And this is something you should know for test 2. How do I go from grams to moles? For N. Well, I have 0.521 grams of carbon dioxide. I want to go to what? I want to go to moles of carbon dioxide, CO2. Therefore, I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And where do I get this? On test number 2 and also test number 3, 1 mole of a compound equals the molecular weight. Yeah. Molecular weight in grams of the compound. And the molecular weight of a compound equals the sum of all atomic weights, which in both test number 2 and test number 3, you'll be given this stuff. In grams. Well, I have CO2, and that's 1 carbon and 2 oxygen. Now, 1 carbon, if you look at the periodic table, the atomic weight, let's find out. I have a periodic table open. Is 12.0. Remember, rounded off to 3 significant figures. For oxygen, 15.999 rounds off to 16.0, 3 significant figures. So I have 1 times 12.0, 2 times 16.0, 12.0, 32.0. You add it up, 44.0. You get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest. In this case, they're both 1. So for every 1 mole of CO2, I have 44.0. Notice this is 3 significant figures. This is 3 significant figures. This is an exact number. So my answer should be 3 significant figures. And now, before, just to be safe, I'll come to my problem again here. This conversion, grams divided by grams cancel out. I'm left with moles. So now I can happily go to my periodic table, my spreadsheet. I didn't put those numbers in. Now I do. And now we'll take plus 0.521 divided by 44.1 grams. And we get that number, which should be 3 significant figures. And I'm going to round it off. Remember, you can round off at each step or at the end. I'm a round off at each step person, so I'll round that off to this. Now, are we done? No, that's why it's 15 points. There's a lot of work. First of all, let me remember what the number was. That would help. I got it wrong. No, I got it. And you might see for this one, use scientific notation, 1.18 times 10 to the minus 2. I see a question or two. Let's find out. Maybe I made a mistake. All right, let's go back. All right, a couple of people asked, was this correct? And that's a good question. I'll check. 1 carbon is 12.0. 1 times 12.0 is 12.0. Each oxygen is 16.0. 2 times 16 is 32.0. Remember, 1 and 2 are exact numbers. These are 3 significant figures. Add it up. 2 plus 2 is 4. 1 plus 3 is 4. And the answer is yes. That should be 44.0. Does everybody see that? We had a question? Am I seeing it right?
Dr. White?
Yep.
I think it was my question, at least, is I believe when you typed in the spreadsheet, you did 44.1.
Oh, thank you.
Yeah. So I just wanted to make sure that that was
Let's
44%.
find out. You're right. And this still rounds off to the same thing. Thank you for pointing that out. Which is why I double check my answers when I do an answer key. All right, so we now know this, and thank you everybody who pointed that out. So this is 0.0188. So what do? Well, we've got this all here. I'm gonna write this down here. V equals, what's N? Well, N is 0.011188 moles. What's R? 0.0821 atmospheres liter. Sorry, I'm writing it mole Kelvin. And then T is 297 Kelvin.
Dr.
And-
White,
Yes.
I think the answer in moles was 0.01.
You're right.
Sorry.
Thank you. Oops, what did I just do there? And there we go. Hold on. I think my mind is on my injection later on, which it shouldn't be. It should be here. Okay. And then what's pressure? Keep an eye on me. That's 0.988 atmospheres. I'm not worried about doing great. It's just being there on time is on my, oh, it's going to be soon. Am I ready? Yes, Dr. White over worries sometimes. Now, before I do the answer, since I wrote it so small here, let me just down here, this you do not have to do, but we have mole times atmosphere, liter, mole, Kelvin, times Kelvin right here, divided by atmospheres. Now let's take a look at this. If we forget about the bottom, moles divided by moles cancels out. And here, Kelvin divided by Kelvin cancel out. And finally, left on top is this atmospheres and liters. Underneath is atmospheres, so that cancels out. And we're left with liters, which is a volume measurement. So we're on the right track. So again, unit analysis, our good buddy, our good friend, helps us out. And now I'm going to go back to my spreadsheet. I see a question. All right, the answer is yes. What I did down here, because I wrote it too small, I was running, this happens sometimes on a whiteboard too in class. I wrote it small to not run into space over here. I just took the units from each one of these here. And I just want to make sure, do I get a unit when I do all these multiplication division in volume? And the answer is, don't know, I better check. So I have moles times atmospheres liter per mole K, that's R, times temperature Kelvin divided by the pressure in atmospheres. Now, forget about the bottom here. If I could hold my finger over the atmospheres, if we just look at the top, moles, and here it's per mole is on the bottom, they cancel out. And then here I have Kelvin divided by Kelvin, that cancels out. So this whole part here and these right here are canceled, gone. I'm left with atmospheres and liters. Atmospheres divided by atmospheres cancels out. And the only thing left standing unit-wise is liters. So I know I did it right because volume units should be in liter. Does that help, Kelly? All right, now let's go to my, oops. Good. Remember, there's no such thing as a dumb question, and you're finding out Dr. White believes in that. So let's do this right. Here I have my moles times R times my temperature. And I'm going to take this number and divide it by my pressure. Dr. White's done these before. And if I round this off to 3 significant figures, I get 0.292. If I do it this way, 0.291, and those are in liters. And therefore, our answer is right up here. And therefore, your burp would have a volume of 0.292 liters or 0.291 liters. And for those of you who are wondering, what does that really mean? Hi, everybody. For some reason, some of the video got lost at the end of today's lecture. So I'm redoing it. And it's just a small little piece. And I was talking about the problem when you burp. And I already did the calculation. And what I'd like to do is go through again how the units right here cancel out. So let's do it. And we have on top here, first of all, mole, then the universal gas law constant is atmospheres liter per mole Kelvin. And then right here, we have Kelvin. And then underneath right here, we have atmosphere. Now, if we forget about the bottom, moles cancel out. Anything divided by itself equals the number 1. And then on top here, we have Kelvin divided by Kelvin. So this whole area here, I'm going to go multicolor on you, is gone. This is gone, and this is gone. All we have left is atmospheres liter, and that's divided by atmospheres. So this cancels out, and all we're left in top is liters, which is what our final answer is. Either 0.292 or 0.291. And that's how you do it. I just wanted to go over that one more time. Don't forget, Monday night and Wednesday nights, I have my office hour. And this Wednesday, after class, we will be having a regular class. I'll be sending out the email for the password for test number 2. You'll have until Thursday morning just upload it with your answers as a single PDF file. And with that, I'm going to say, gang gazoon, goodbye, and I'll see you on Wednesday. Bye.